Hello, everyone. I welcome you all to the inaugural session of Kent Seminar Series for the spring semester 2024. It is my honor to introduce our first speaker, which is Dr. Angeli Jayme. Dr. Angeli Jayme is a research scientist at the Illinois Center of Transportation at the University of Illinois Urbana-Champaign. Her research interests include tire pavement interaction, asphalt materials, pavement rehabilitation and preservation, energy harvesting and smart mobility. She holds a BS degree from the University of Nevada, Reno, and master's and PhD degree from the University of Illinois, Urbana-Champaign, all in civil engineering. Also, Dr. Jayme is one of the core planning members of the Illinois Autonomous and Connected Track. She is the recipient of American Society of Civil Engineers Transportation and Development Institute 2023 Outstanding Young Member Award and Academy of Science and Engineering's Associate Member Award. Please join me in welcoming Dr. Angeli Jayme.
Assad. He's distracted now.
Oh, sorry. I would ask Professor El-Qadi to also have a word, please.
Assad is ignoring me, so I have to remind him. So, thank you. I think I thought it's very. Is the camera for the camera? Okay, of course. I thought that we should introduce Angeli properly. So Assad, he has to do the professional and appropriate introduction. And I do appreciate that, Assad. But on a side note, I should I guess, say a couple of words. Angeli is not just a former student. She is a close friend. That's at the personal level. And we have been working together for 10 years or maybe before. But most importantly is at the technical level. I was very impressed over the years how she grew up from a person who does research to a person who can lead and a person who can work with everybody. And it's always a pleasure working with Angeli. So here's a trick. When you work with Angeli, if she says yes, this means that she agrees with you 100%. If she says yeah, this means that she does not agree, but she's politely telling you, you know what, I don't want to say no. So all I want to say that she's one of my favorite people that I ever met in my life, and that should say it all. Angeli?
Thank you so much, Professor, for that nice introduction. And now everyone knows my secret in the way I say yes. Thank you for this opportunity, and I am quite honored to kick off the 2024 Kent Seminar, especially with the new setup here at ICT. Thank you so much. The lineup that we have for this semester is quite extensive, and I feel quite honored to be considered to be one part of the list. And given that the theme of this Kent Seminar is modeling and mechanics, which is near and dear to my heart, I thought it'd be appropriate to give you at least an overview of some of the tools that we have created at ICT, and particularly give you a sense of how we really dive deep into pavement analysis using numerical modeling. To set the tone, the problem that we have at hand, which we encounter every day as we drive to work, or even when you walk on top of pavement, is it's a loaded pavement problem. Three of the main categories that drive this, not to our surprise, is the load itself, right? The magnitude of the load, and that's why when we design our pavements, is the truckloads that we're really more concerned about, more so than the amount of passenger vehicles that travel. The pavement structure, and that's really driven by what configuration do we have? Do we have concrete? Do we have asphalt? The associated layers in between, and even the structure, if it's highway or airfield, because some of the thought process in designing such pavements also differ, but also the climate of how that pavement in terms of the material and as a system under that heavy traffic loading will sustain the load over the design period that we really designed it to be. And particularly, I want to focus our attention to tire pavement interaction, which is what I've really focused on in my time as a researcher. So going into that two-body problem, I hope you can appreciate this picture from Encanto by Disney. It's one of my favorite movies with my nephew. If you haven't watched it, please do. I'll watch it with you. And really the idea is similar to Louisa carrying the system or body of donkeys, right? Like her muscles are reacting to the excitation that's being given to her, similar to how a truck tire, a load is loading a pavement in this two-body problem domain. And so how do we do this? The modeling framework, as we can tell, right, similar to when we trained or even when we do equations, there's an input side, there's a black box of equations that you plug and chug, and then there's the output that you expect to learn more about going through that framework. So in this two-body problem, as I've mentioned, the pavement structure, configuration, thicknesses, composition is one of the inputs. The associated material properties for each of those layers, because how that behaves depends on the material that is being subjected to and how that material is being impacted by the environment, whether it's a combination or singular individual contribution from temperature, even inundation or flooding for moisture damage and such. And I cannot echo enough the loading itself, because the magnitude compared to the other components really drives this excitation. And we can even further dissect this load, not only the tire load itself, the inflation pressure and some of the rolling conditions, which later on in the presentation, we have some data sets to quantify how the loads change as a function of such metrics. And all of those input into our main tool, which we've used, and among other researchers who've also used other tools, but our point of interest here is using the finite element method as our main means to identify how all this clustering of inputs into a loaded pavement problem really helps us understand the behavior of pavement. And at the end of the day, why does that matter? It's because, as a pavement engineer, a designer, we have to go back to the design that if you intended to withstand X amount of loadings, X amount of seasons, it should, because you know the inputs and what it's going to be subjected to. So we're relating it back to what's done practically, which is to anticipate when the pavement will fail over time, over a given number of loading. I will do a quick sidebar, especially that this is a modeling a theme for this semester, and also echoing this ongoing effort with the ASCE TNDI Highway Pavement Committee, led by Jaime Hernandez from Marquette University, among a list of really nice colleagues who's also working with this, and in collaboration with the EMI Engineering Mechanics Institute of Pavements Committee. And I just really want to share this, for practitioners, researchers at any levels, for students, the idea and the definition of verification and validation. And I really bring this up, I won't go through the details. I just want to preface it, as we're embarking into modeling, it is very critical for us to understand the difference. Verification entails that your math, your algorithm is well represented by your code. So you're verifying that the physics of those equations are actually representing what is coded, and that's verification. Validation, on the other hand, is being able to now, after that code is verified, that it can now represent the reality. And these two terms are usually interchanged, even on papers that I have reviewed. And the importance is for all of us in this realm of whether it's pavement structure modeling or any type of modeling problems, for us to be on the same baseline so we can help each other make our models more credible and review each other's work with the same baseline idea and terminologies that we should be in agreement. And just something to look forward to. The paper for this work, which is we're offering to the community as a means, as the initial baseline, that if you were to check or identify some of the topics that I just mentioned, we'll be sharing. And again, the idea is, as a group, it's not the intent to tell how to model, but in case you are intending to model, here are some of the critical steps and jargon or terminologies that you should know, because there's a framework that has to be followed appropriately. Another thing that we emphasize, and you'll see in my letter presentation, is being able to outwardly say what is the intent, what is the constraint of the model? Because at the end of the day, there's not a single model that can do all the problems. It's bounded by the build of the model. So being able to communicate that clearly to the community helps us make use of each other's models because we know the limitations in what the intended use of such model. We also offered some learning exercises, not only in asphalt pavements, but also concrete pavements, material modeling. This is past finite element modeling, which I'm presenting today. And as I've said, just as a baseline use of such framework that we are not creating. I think even the Department of Defense created this way back in the early or mid 70s. So this is nothing new, but it's something that we tailor for our needs for pavement engineering. So just a quick sidebar for that one. So let's go back to the two-body problem that I've mentioned. The first body we're now going to take is that from the perspective of the tire itself. A quick introduction, if you have not seen, this is a dual tire assembly. If you ever see a semi at the back of it, a trailer, this equips half of the axle. Just to mention, this is a dual tire assembly for a conventional semi. So what did we do in this work? As I've said, loading excitation is one of the main governing factors to make pavements behave or respond. And so one of the efforts that was done several years ago was to send these tires to a facility in South Africa to actually obtain measurements, indirect measurements of the contact surfaces. But the idea is that on the top left, you see a grid of pins. Those are measuring pins. So the idea is as they deflect, there's a voltage, and that relates all the way back to the contact forces and stresses. And the idea is now we have an input, measured input for a pavement model that we can excite and understand how that behavior. Because we have sent that to South Africa, we also use Smithers laboratory to send a wide base tire and a dual tire. Today, I'm only talking about the dual tire assembly, the actual cross section of the tire. And as you can see here, the reasoning for that is for us to actually model the tire physically, and the layer differences that you're seeing in the cross section were actually modeled in the tire, including the reinforcements that's going circumferentially. So what did we do? We assumed that the tire is hyperelastic. And when I say elastic, I think we're fairly familiar with elastic, right? There's a stress and strain response. The hyper part comes into the fact that rubber lives in a large deformation domain. So it's just a little bit different characterization, but the same premise that we're staying at the elastic realm of once you release the load, there's no deformation, but just larger deformations. So in this work, numerically, as you can see, we imposed different rolling conditions when a tire is braking, accelerating, cornering, and here are the actual snapshots of the contact stresses, the vertical contact stresses, if we were looking from the bottom of the tire itself. And we also included numerical matrix varying not only the rolling condition, but also the speed, the applied load, and also the tire inflation pressure. And for the brevity and the extent of today's presentation, I couldn't include it all, but I'd be happy to talk. Or I also noted the report that details all the nice details of this work that was done earlier on. And I mentioned verification and validation and the importance of ensuring the accuracy of your model, because at the end of the day, garbage in, garbage out, without you properly bounding and creating that model appropriately. So just a quick check that we did perform calibration and validation of the model that I just showed of the tire pavement model, and the measured deflections and the contact area might match quite well, 5% and under. We also check the maximum vertical contact stress. I have to note that as I've said, the contact stress were not measured because the pins would deflect, and that what you're measuring is actually a voltage. So there are steps in between to even get to the contact stress. So one of the notion in having a relatively high, but still, surrounding around the unity line for the measured, for the contact stress comparison of the measured and the calculated, there is a variation of influence area for the pins. And what I mean by that is the absolute contact between the measuring pin and the tire differ. When you're converting from the voltage, the voltage all the way to contact stresses, it assumes a uniform influence area, which means the pin is always in contact. which is not necessarily true, as you can see here, where it varies from, right? You can say 0% for this pin all the way to 100% in the middle of the tire. So that's where some of these inconsistencies may stem from, but the fact that they're hovering around the unity line gave us a green light that this is a fairly good model to move forward in predicting contact stresses. Let's further complicate and make it more fun, because so far the model that we saw previously was just dealing with the mechanical deformation. I guess I'll use my cursor in case we have people online. The mechanical deformation model was the one we did previously with the hyperelastic tire. But as we know, asphalt concrete, akin to rubber, is not only influenced by how fast you're loading, but also the temperature. And so the notion was, well, what happens to that distribution of contact stresses in 3 dimensions, vertical, longitudinal, and transverse, when we further compound this problem and make it a coupled problem with thermal and mechanical interaction. And to account for thermal exchange, we did assume some boundary conditions, convection, so anything that's exchanging temperature with a fluid or air, so that's convection, and then conduction within that different components. If you remember, our cross-section previously of the tire had different components, so conducting within those different components inside the air. Maybe one thing you can think of as you're traveling more after you start your car, your tire temperature inside is actually heating up. So that operation temperature needs to be accounted for and how it influences the tire itself, and also conduction between the tire and the pavement surface. So given whatever the tire is steady state, as it's starting to be in contact with the pavement, then there's also exchange happening whenever they're in contact. And both of these are happening together in this coupling scenario. So the first question was, does it matter? Was our first question. And here's just a quick picture that I want to show you that the answer is yes. The one on your left, the blue one, is a pre-roll, and then simply after 1 revolution, there was a change in the tire behavior. So the first gate for us was, okay, well, it seems it is a little bit merited to keep following and see this thermomechanical coupling for a tire pavement interaction. So we further checked sensitivity analysis, and I do want to comment that maybe some of these combinations are not realistic, but we wanted to see how sensitive the model is when there are changing parameters. In this first one, this first line of plots, what we're seeing from left to right hand side, we're seeing the distribution of contact stresses for the vertical, the longitudinal, and then the transverse contact stresses. And simply this frequency representation is, if you were to take all of the contact stresses within an imprint corresponding to this value, how much they are occurring within the imprint. So there's no, the idea of spatial domain no longer matters here, but we wanted to see how the distribution is changing when we're changing temperature conditions. And in this low temperature, we maintain the road -10, fair, again, low temperature, the ambient to 0. And again, the relation with it, we didn't establish, we just select crudely to see the behavior of the model itself, and we changed the inner tire from 10 to 65C. Again, highly unrealistic all the way to 65C. Usually the operating temperature normally lands around 35, but we just wanted to see what's going to be the difference. So in the temperature plot, we see that the temperature of the tire itself, when we subject to these different boundary constraints, does change. So that's good. The model is actually performing with respect to what's it's being bounded by. The differences as the vertical distribution here are overlaid. It's not as big of a deal, and likely this is because we're at really low temperature. There's not a lot of deformation that's happening in the tire to actually redistribute that same load at varying levels of contact stresses. So now, well, what about when we do closer to room temperature, 25C? So we maintain the road surface at 25C, maintain that inner temperature of the tire itself at 35. As I've said, that's a more conventional operating condition. And again, unrealistic, but seeing the sensitivity of the model from -10 to 65, see when those 2 parameters are kept, we see that the temperature, it's highly redistributed, contrast to the low temp where it's the same trend, but it's just shifted. Now it's completely different animal where the distribution and even the shape has changed significantly simply by changing the ambient condition that's outside of the tire when it's rolling over a pavement. And to us, what became more important, because this is free rolling, the changes in the longitudinal, the second and the third plot, which is the transverse, are relatively overlaid. These two are also conventionally much lower than the vertical contact stress. But how, to us, what was nice was, okay, the high magnitude of the vertical contact stress, there's a lot of changes happening and almost like a flip at pretty high. 1 MPa is around 145 PSI, where at lower temperature, where you're getting more lower values of contact stresses, and that's because you have a higher contact area that you're reducing that contact stress value. So that same load you're distributing over a higher contact area. That's why they're shifting to lower values of contact stresses. Now on the blue, which is the lower temperature, red is the hottest temperature. The blue, on the other hand, has lower frequency of lower vertical contact stress values, but higher all the way to 1.5 megapascal. And that physically is because now we're constraining the tire pavement contact area to be less because we're not allowing it to deform. So in essence, although I have said the disclaimer of some of these combinations should actually be better related, right? There's a relationship between the ambient and the surrounding, but we wanted to check how feasible even for the model to observe such differences, even though such combinations may be unrealistic. And this becomes important, going back to the framework that we saw earlier on, is loading it back to our pavement condition. And this is a snapshot. So seeing how that contact stress driving that load excitation and response excitation, how we will change the responses within our pavement model that's a layered system. And on top of that, I hope the video will play. Just a side note, I saw this in YouTube. It does say it's for sleeping and relaxing. I do not use this for myself to have me sleep and watch a bunch of trucks travel over the road. But I thought it was kind of fun. But I'm bringing this up because, you know, we've gone through some of the other factors, but we also have to take into account that traffic moves continuously. And so one of the means for us to have characterize that is to actually impose a smooth entrance and exit to the load. And it's akin to if you were to hold yourself in place in the front here as your point of analysis, right? As the load is coming closer to you, the response should be increasing when it's right above you and decreasing as it goes. So that's the reality that we're incorporating the model itself to emulate this continuously moving load to further realize, you know, what's really happening out in the field. So that's the first perspective. We have captured a tire model because our load excitation governs how pavement should respond. So now let's take it from, you know, the other body of the two body problem, which is from the pavement perspective. And here's just a quick example of maybe a typical flexible pavement. So what are the assumptions? So this close, as I've mentioned in the verification validation work, it is really critical for us to disclaim the assumptions as it relates to the constraints of any model that we do. So in the final ML model for the pavement, we are performing a dynamic implicit analysis to account for inertia, the material characterization from the layers that we saw previously. We do account for linear viscoelasticity of asphalt concrete as it's loading frequency and temperature dependent. Whenever you have a thinner surface layer and you have an adjacent granular layer, it has been found and well proven that the stress dependency of those layers, it becomes really important. The thicker it is, the farther it is from that stress value, say deeper, let's say 10 meters into a highway pavement, you can assume it's a linear elastic because stress dependency no longer matters. And that's why there's a quick note here of thin or thick pavement structures. I hope that I've convinced you the importance of three-dimensional contact stresses and the tool that we have to actually get there from the previous slides that we have, and then the continuous moving load implementation that we do for the smooth and entry and exit of the tire to really emulate what's happening in reality. And for us numerically, that's just really doing a smooth transition over the elements in a finite element model. We also want to point out that I've talked about boundary conditions, so setting up your model itself, not only for the reality, but abating any numerical errors. So what I mean by that is I could inherently, create a new model which is more narrower, but then we're going to run into boundary condition issues. And so that's why we've elected to use infinite boundary elements to emulate far field regions, similar to what we have out in the field, right? Where super far from the load of interest that it should really taper to zero because it goes to the core of the earth and there shouldn't be any loading felt that far. And then also a last component is the layer interaction. So the bonding, if you have multiple AC layers, and then also a friction condition whenever you have an AC to granular and granular to subgrade and so forth. So these are just really the nice factors that we've incorporated in the model with the intent to really model reality as close as possible. So then the tool becomes very useful for us to understand pavements really deep into any of the layers. So I've mentioned the importance of pavement analysis, and I want to reel us back to what's done conventionally and what are some of the responses that are of interest when we do pavement analysis and evaluation. Two of the critical ones, and maybe you may remember this from your statics or mechanics courses, is tensile strain at the bottom of the AC, right? When you have a beam, the tensile at the bottom of the beam becomes important. Similar premise for pavement responses. The vertical compressive strain on top of the subgrade tends to govern for rutting, and the tensile strain is with respect to fatigue cracking. So conventionally, these are done in the field and we're calling transfer functions. Maybe you've done MEPDG or similar type of pavement analysis schemes. And the idea is from this single run of responses, a quick snapshot of how the responses result in terms of strains. We use transfer functions to predict all the way into failure with hundreds of thousands of repetitions over many decades of analysis. However, one of the things that this approach, although has been very useful for our field, some of the drawbacks is we're really missing not only the three-dimensionality, but the fact that when you have pavement damage, it doesn't stem from a single point. It's because of the contribution of what's surrounding that point leading to that failure. And so we wanted to leverage the fact that we have a 3D model. We can calculate that bulk response. So the next question is how do we do that? One of the methods that ICT has come up with is we termed it as the domain analysis method. And simply put, it's really a means to tell you the bulk pavement response in 3D and not just relying on a single point response. And I'll have some examples why we thought this became quite important. The GIF you see on the right, you see P is your mean stress, if you may remember from mechanics, and then Q is your shear indicator, which is, these are just really combinations of your principal values, sigma 1, 2, and 3, or epsilon 1, 2, and 3, just mean versus shear. And the GIF is changing because these are actually different cross sections along that wheel path that we're loading. And what I'm pointing out is depending where you are, similar to where the pavement is loading, we can see how complex the nature of the behavior of our pavements. And that's why we became more intrigued. Well, why not capture and be able to describe our pavement, capturing all these complexities and compare it relatively to a case. So we did just that. The PQ is our main metric that we're using, which multi-axial because it's in 1 and 2 and 3D. We have discretized the pavement domain, as you can see here. There's zones 1 through 9, and this is really following similar premise to pavement design, where we probably anticipate that compression is going to happen within the Z2, closer to the top, and then tension is probably going to happen closer to zone 8. So that was kind of what's driving that, and we did test appropriate boundaries and extents of this vertical and horizontal lines to make it more representative and not as a function of how big or small the box is. And after we partitioned saying, okay, this group of points in 3D belongs to zone 2, we had to penalize the points. And what I mean by that, when you have high shear and high compression, you should probably penalize that contrast to the middle of the pavement, zone 5, where they're slower. So that's the idea of the failure criteria. And finally, we combine all of this nice process into a single value. And mainly because that it becomes like a relative value. It's relative to the case that we're comparing to, and I hope in the next slide that will make a little bit more sense. So in an FHWA project, we compared for highway pavements, NGWBT is new generation wide base tire, DTA, dual tire assembly, the picture that we saw of that half axle tire that we saw. And the steer tire is the one that's really put in the front of the cab, which is in practice, it's one of the dual tire assemblies. So the same exact tire is just one. So following the pavement critical responses, so there's their single point, very direct response. So 3-3 is along the transverse direction at the bottom of the AC when it says AC. The transverse tensile strain on the surface, and 2-2 is your vertical. So these are your vertical strains within the top of the AC, the base and the subgrade, and also shear. That's a vertical shear within the AC. And because before we dive into this next part, I want to point out the key difference to, so these are two different tire configurations, wide base tire and dual, but also the steer, since it's only one tire, it's actually a little bit higher. It's not just half of the dual 44. And what we can see is because there are a difference in the tire itself, right? New generation is one wider tire compared to two of them, a little bit narrow dual tire. There's that redistribution that led to these differences between the wide base and the dual. And we're using the dual as the reference. So for instance, even the shear strain for a wide base tire could be, I don't know, between 60 to 70% higher than the dual tire assembly, simply because of using that one tire. The steer, on the other hand, it became also higher than the dual because it has a higher load for a single tire than a single tire of the dual. So that's great. We're able to capture that. But now leveraging the domain analysis that we mentioned, we also introduced two other zones, which is combining half of the Z zone 2 and zone 5. And the next slide will help us appreciate this more. But the idea is we're hoping to capture, well, what about since it's non-uniform, the left side and the right side. And what we see in the domain analysis scalars, the D1, which is the right-hand side, the green plot here, for the wide base tire could be all the way up to 70%, much greater in the bulk domain than the dual tire assembly. And some of that impact, even way deep into the subgrade, could be 20%, which could be missed by these lower responses. The steer, similar premise, because of that high load closer to the surface, we see an increase relative to the dual tire. And because lower responses deeper into the pavement is governed by the load itself, it has a lower load, 30-44, and that's why it's less than 1. Now, another conventional scenario that happens in the field is having different inflation pressure for semi trucks. And that happens because truckers or whoever's maintaining the semi, it's hard to get to both of the tires. So usually one is underinflated or there's difference in inflation. And as you can see here, following these critical responses, it's okay if we forget what these variables now are corresponding to, but uniform versus the differential inflation pressure scenario no longer change between our critical responses. So inherently, that doesn't make any sense in terms of if there's a difference in the loading conditions, should we anticipate a difference in response? Although closer to the surface in shear, there's a little bit of difference, maybe 15 to 20% here. And so remembering the left and the right-hand side of that partitioning of the zone in 5, we really like that the domain analysis was able to capture the critical difference in, this is the higher inflation tire and this lower inflation tire for a bulk response when you have different inflation pressures. Now, turning that a little bit, I don't know, in the talk premise, we also have done airfield pavement. So we saw highway, but I also want to turn our attention into airfield pavements. And taking a step back again, we're looking at contact stress data for a turning condition. We're starting with the free rolling. We're focusing on the pink with horizontal dashing. As you can see, it's symmetric, right? Your longitudinal, when you add it all together, it should be fairly symmetric because it's just moving in a straight line. However, when you start turning, even if you start leaning your body to one side of your left foot, and especially if you're moving in circles, what we anticipate is as you increase that turning propensity, that symmetry now starting happening. It's no longer symmetric because the problem is no longer symmetric. And that's also even realized in terms of transverse contact stresses, that as we increase the slip angle, and here for A380, which is the aircraft of interest that we modeled, or we consider in the pavement model, it's 6% is the recommended safe slip angle per airbox condition. As you can see here, again, because we're turning that condition, the representation is a transfer contact stress also increasing with that level of turning condition. So going back to the domain analysis that we created, what does that mean in terms of your AC, D1 and D2 partitioning, the bottom of the AC Z8, and also the base and the subgrade? You see that as we keep S1 is a tire inflation pressure, V1 is also a given velocity. So holding those two in place, simply changing the level of turning from 0 to 2 degree and 4 degree, we see a significant increase in both behavior and most dominant within the AC condition. And then when we increase the inflation pressure S1 to S2, so it's an increase that is further exacerbated all the way to 1.9 times greater than the reference condition. And to further to add to that, one of the ongoing projects that we have with FAA is utilizing their construction cycle for many data for flexible pavements. And one of the things that we ran into is some of the measurements we weren't able to utilize fully. So we borrowed, our tools in numerical modeling to understand for a tridem or a tandem condition. However, the issue with this is it becomes very computationally very expensive. The runs that we've seen thus far of the pavements I've shown you in highway and airfield are single tire simulation, and those could take days depending on the build and the complexity and how fine the partitioning are. Imagine further lengthening that when you have a tandem and a tridem, and you have to physically represent the distance between those two axles, let alone the one that's laterally available to have a full axle. That becomes very, very unfeasible. So one of the things that we recently established at ICT is the load pass approach. And how I can explain it better is, so this is a video that I took when we visited the FAA facility, where you see that, in our viewing window, you see the entrance of a single tire, the tandem, and then the tridem. And that's exactly what we did. We were able to reduce that roadway length in the model, similar to this viewing window that we have. And the idea with the load pass approach is when we manipulated the loading condition so that the pavement is able to experience the tandem or tridem axle loading without needing to extend so much meters of pavement, which is unfeasible, and we don't have time to wait for a single simulation for weeks, if not months. But since our pavement model conventionally have been tried and true, and many applications of validation with the Ohio section, Davis, Florida, and so forth, we had to make sure that we're not violating anything in this new load pass approach. So some of our checks indicated that we reached steady states. Their responses are also preserved, which is great, so we can move forward. Another thing is in terms of the history, closer to the surface where you will see this loading more predominantly, we did capture, the passage of the tridem, and then more than a meter into an airfield pavement, you see that interaction between the axles, which is also nice now with this new approach. But really what drove us is significant time savings. I will say that the conventional approach is infeasible, even with using a supercomputer, just because of the extent of the model. Versus with the load pass approach of that narrowed window, it reduced to less than a day. And granted, this will have a little bit of variation depending on the build that we're considering. And one of the efforts that we're doing right now, too, as part of a regional UTC with CCAT, is implementing the load pass approach to hopefully combine that with rutting in terms of cyclic loading for within a smaller model domain. So those are the two tire pavement body interaction that we have thus far in terms of the tools. In my last few slides, what I wanted to bring up, and I think maybe many of us have attended TRB. If not, this is something that is in front of us now as transportation engineers, is how do we help battle climate change and decarbonize as one of the main contributors to climate change. But for me, what I can contribute is maybe from the tire pavement perspective. So it's no surprise, right? This is like the general metric and what it implies in terms of temperature, precipitation, and sea level rise. So now, two questions is coming as pavement engineers: what is the materials or configuration that we need to account for this temperature increase because of aging and so forth, and also inundation or flooding when it's subjected to extreme events. One of the things that the US DOT has been keen on is also pushing electrification as one means to battle to decarbonize. And one of the nice maps that they've created is, as you can see here, where the green they've indicated as a corridor ready for electrification and corridor pending for the brown ones, where I'm highlighting here where Illinois, we do have a suite of corridor ready and pending highways available for this electrification. And particularly one of the projects that we're doing right now at ICT in collaboration with Marquette University is the question of, if we have heavy duty electric trucks, no longer need fuel, no longer need the engine for a combustion engine, but now we're replacing it with an electric engine and also the battery, and the placement of that battery. Are our roadways enough to sustain that load difference? And on top of that, because it's an electric vehicle, I don't know if you've been in a Tesla or even electric vehicle, the access to that acceleration is much faster than a combustion engine. So another question is, well, will shearing be worse? So again, the main question we're trying to answer is what we have enough for the pavements to sustain this potential increase in load, and combined with high acceleration or deceleration? If so, by how much, or if not, what should we change? And so I will go back to, as I said, our tried and true and nice tool in our loaded pavement simulations, where we incorporate the materials, the loading, but now we're changing the loading to heavy duty electric vehicle. We're considering typical sections here in Illinois, and even including a composite pavements, because we have a lot of original concrete pavements that are now overlaid. That's also of interest, and setting a temperature condition, and again, answering, will it sustain these new type of loading conditions that we're subjecting our pavements to? And hopefully some of our findings may help identify some potential, thoughts on change in design, maybe how rehabilitation over time needs to be done. And we'll also be doing a life cycle assessment to incorporate and identify the environmental impact as we're delving into this topic. And so today, I know that was a lot of information. I will not give any quiz, but hopefully in this really brief deep dive into the tire pavement interaction realm, what did we see? One, we saw a validated tire model to generate contact stresses that incorporate rolling condition, braking, accelerating, cornering, the applied load, inflation pressure, and velocity, and also further compounded that with thermomechanical interaction when you have temperature into that mix. We have a validated pavement model, so now we can use that contact stress input to excite our pavement responses along with environmental loading in terms of temperature. And we saw one of the means to identify or understand how both pavement response really behaves through the domain analysis, and leaving everyone, including myself, of what should we be doing, as we move forward to the future in near term in decarbonizing, and particularly of interest to me. The project that I've mentioned is the heavy duty EV truck impact of pavements, but a personal interest too is compounding that impact. And I think some of our speakers are also going to be maybe hopefully talking about this, is impact of climate change on pavements, and which is a really wide open arena for all of us to tackle. And with that, that's the end of my presentation. Happy to take any questions. I don't know if there's Zoom, but thanks so much.
We have time for some questions to Julie, so.
Angeli, very tough. You were mentioning higher stresses and higher loads towards the end. Does this mean that we are going to have to think, how we design pavements and how we design asphalt mixes and how.
That's one of the questions we're trying to answer. So one way that to help us identify that is some of the pavement structures and mixes that we're incorporating to our numerical are the current ones. Some are, recently overlaid, one of which is actually your project, the SMA. So that's a newer-ish like technology type of mix. There's one full depth or typical pavement that has been there a while. So I guess we don't have that answer yet, but we're hoping through our findings and loading this battery replacement of increase in load and increase in acceleration, how the pavement responses are. We are running the simulations actually as we speak with Johan Cardenas. So hopefully we'll be able to share more. But the first question is the current build of the current materials and the structure that we have. How are the responses? Will they be enough? That's something we're answering. If it's not, then we'll have to do a second question to you. Your question is, okay, if it's not enough, what would be enough to sustain that increased load and increased exertion? So I don't have an answer yet, but we will have one.
Questions?
Thank you so much for the Angeli. An idea came to my mind now that we are trying to explore the implications of having different demands, specifically sections like intersections, exits, entrances. And I was looking at the considerations of the coordinate cases for your tire models, and we have seen that it's evident that we have a redistribution towards one of the sides of the tire. And maybe this is not a concern when we simulate at very low speeds, but if we are trying to simulate vehicles going at highway speed, do you think we should also account for a distribution of the axle load between the tires? Because as we are entering a curve, the vehicle leans towards one of the sides and maybe the distribution is not equal anymore.
Yeah, no, that's a good question. And I know I'm not an expert in this, but in practice, how ramps are designed, some of these are accounted for because of that shearing maneuvering that you're describing. On main line, maybe not so much, right? Because it's not so much of a big turn, but more a gradual shift because driver behavior also don't want to change lane quite quickly. But there is, I believe there's special considerations with ramp design. I don't know how much in terms of the redistribution. Maybe that's something that we can explore, especially now we have that full axle tool that we can do. But I do want to note for airfield pavements on the other hand, where this work stem from, high speed becomes important when it's landing. So when we presented this to the airport compatibility committee, when it lands, and we feel this too, like you jiggle a little bit and there's high shearing in that area, which is also specially designed or has a special accommodation because of that high speed and high shear. And that's contrast to a taxiing, which is low speed and high shear. So there's a little bit of how it's being accounted for, but hopefully through our tools, we can dive deeper on how those metrics or like design processes need to be better accounting for that. Yeah.
Any more questions? We have 2 minutes. Angeli, we can ask one question. So usually for the asphalt layer, we also sometimes have like binder layer and surface layer. And how is that accounted in like the models that you showed, and how complicated it is to consider this?
Yeah, so for the airfield pavement, I think we may have up to 2 layers, but for highway pavements and the FHW will work, and even some of the data sets that we have considered more than one AC layer. So as you said, we have a surface, intermediate, and also a binder layer. We're accounting for that, so the given thicknesses that they have, and then the corresponding material properties that they should. One thing that we also account for, and maybe we can explore this in detail. So far, we assume those as a fully bonded layer. So now with high shear, I reckon that delamination can happen when you have really low bonding between two. That's something we have not explored right now, but hopefully with the tool we can dive deeper into when you have those multi-layer high shear and high load, say for EV trucks, and how potential delamination may occur. Yeah, that's a good point.
Yes.
Just a small question. Actually, obviously, over the past 6 years, you've done a lot of work, and I getting a very accurate way of determining stresses on pavement and through the tire and stuff. How do you see this integrating with, let's say, any contractor or consultant who wants to design a section in Illinois? Because obviously the barrier for entry is like extremely high with all the equipment and stuff that you're using. So how do you see this like finding a way into like the mainstream market when it comes to pavement design, or how?
Yeah, no, that's a great point. And some of the efforts that we've done in the FHWA, one thing to account, say, for wide base tire, because most of the design premise is a dual tire assembly, what's conventional. So in that work, we have offered adjustment factor. But I think what you're leading into is, you're absolutely right, like agency, which is our main customers, right? We serve the public. I can't just say buy a finite element, put these inputs, that's not really feasible, and that's not the appropriate matter to do that. One of the things which I'm not an expert of, but at least our ICT or our group has been moving forward, is tagging the power of data with finite element. So in the recent work with the FAA of that TRIDEM configuration, we provided that three-dimensional responses to a physics-informed neural network to handle data well and be able to predict within the domain of metrics that we have in the simulation. But one intent is, one way is, can we embed such neural network in a design, could be one. Or another thing that we're also thinking is maybe even having a more simplified approach and narrowing it down to a plug and chug equation to allow us to get there, utilize this nice data without needing, the expense of doing finite element or even neural network as some of the approaches.
With that, we thank you again. Thank you everyone for taking the time. See you next week.
Hey, hello, before you close that,